Alright, welcome back everyone. Here is our next example on U substitution. So once again, a complicated looking integral which would have been impossible for us to solve without the method of U substitution. But now the goal is to try to rewrite this integral in terms of a much simpler looking integral that has the U variable. So I'm going to let U be equal to x cubed plus 1 because I want to visualize this as a square root of U. That will be so much easier to integrate, right? And then hoping that along the way x squared dx can be written in terms of the U variable as well. So this integral will have a square root of U in it in a moment. But what am I going to do with x squared dx, right? So let's manipulate the U a little bit by differentiating it with respect to x and multiply both sides by dx. So du equals 3x squared dx. And so if this is replaced with square root of U, I need to know what to do with x squared dx, right? So I come over here, solve for x squared dx. X squared dx equals du over 3. Okay, so I will replace x squared dx with du over 3, and constants are easy to deal with because they can be just factored outside. And let me write this as u to the 1/2 du. So now I can anti-differentiate this much simpler looking integral. So it'll be u to the power of 3 over 2 divided by 3 over 2, or times 2/3. So now I have 2 over 9 times u to the power of 3 over 2 plus c, and as always I will replace the u back in terms of the quantity u in terms of x, which is x cubed plus 1. So we're going to have 2 over 9 times x cubed plus 1 to the power of 3 over 2 plus c. Alright, so take a look at the steps from the beginning to the end, and ideally the best thing to do would be for you to redo the problem this time without looking at the solution, to see if you can repeat all the steps, if you can reproduce the same solution. And again, in the beginning these questions might look a little bit confusing, but it's a repetitive process. You're going to see that the same technique is applied from one problem to another, and by the time you see like 5 examples of this type, I think you're going to feel a lot better. I think it's going to make a lot more sense. In the beginning it may be a little bit confusing, so bear with me through the next few examples. And again, ideally stop the video, pause it as many times as you need to, see if you can figure out the next step before I write the next step down. And just to reiterate something, so we're trying to go from an integral that has x's but a complex integral to something simpler that is easy to anti-differentiate or integrate. And let me give you a tip as to how you can choose your u variable. Let u be a quantity so that when you differentiate it, like if you use x cubed plus 1, when you differentiate that, we got 3x squared, that the derivative of the u should be already embedded in that integrand. Okay, so the derivative of u is 3x squared, and there's already an x squared in there, right? So the constant is not so important because we can manipulate the constant, but everything other than the constant should already be existing in the integrand, so that this question is solvable with the U substitution method. Okay, now part B of the problem is asking us to do the same problem but from 0 to 1. In a situation like that, first you would have to solve the entire problem. Assume there is no limits of integration. Okay, finish the problem. Since we've already done that, I'm going to write it down. So this one was copying the answer from the line above. And at that point, go ahead and plug in the limits from 0 to 1. So for this question, we had to basically first solve the entire problem using U substitution. Right? If you have limits of integration, in the beginning you would ignore the limits. You would just solve the problem with the technique of U substitution, and only at the end, after you've brought the x variable back, you would put the limits from 0 to 1, and now you're ready to evaluate them. And 2 over 9 can be factored outside, so plug in a 1 for x. 1 to the third is 1. 1 plus 1 will be 2, so you have 2 to the power of 3 over 2. And then minus plug in a 0 for x. Then 0 plus 1 is 1, so we're going to have 1 to the power of 3 over 2, which of course 1 to any power is itself. So here's going to be our answer, 2 over 9 times 2 to the 3 halves minus 1. And you can get a decimal for that if you like, and 2 to the 3 halves can also be written as, that is the square root of 2 to the third. So you can write this as 2 times 2 times 2, and 2 of those can get outside as a single 2, so you can also write it as 2 root 2, right? So this will be another way to leave the answer, 2 nines times 2 root 2 minus 1. Either one is okay, and you can also get a decimal answer, but sometimes I will ask for an exact answer, so it's important to leave the answer in one of these two formats up here. Okay, so that was an example of U-sub involving limits of integration, and what we've seen is that one of the approaches to solve it is you first do the problem without any limits, and then you plug the limits at the end. There's another approach to this when you have limits of integration, and that is you would stop right here when you have u variable, and you would convert your limits to the u variable. I'm going to give you more examples like that later on, but for the moment, let's practice this technique. If you have limits of integration, bring the x variable back and plug the limits in the x variable. Okay, another example with u substitution is the integral of 5x times the cube root of 1 minus x squared. So think about it. Which variable here would you like to select as your u variable? So when you put that in there, you want the integral to look much simpler, and also whatever you let u be equal to, its derivative should already be existing in the given integrand up to a constant. So think about it. So in this case, you might think about let u be equal to 1 minus x squared, and du is negative 2x dx. So what I did here was, in my mind I said, okay, du dx equals negative 2x, and then multiply both sides by dx, so du equals negative 2x dx. If you'd like to see that other step, by all means put that in, but going forward, typically we write it in this notation, du equals the derivative of the right hand side times dx. Okay, so I come back to here, this middle portion where you have cube root of 1 minus x squared, that's the part will be cube root of u, because the inner part is what we call u to be. And then the 5 can stay as a 5, and the x dx, I should come over here and solve for x dx. X dx can be replaced with du over negative 2. So first I put that inside, but in a moment I can factor the negative 2 outside. Okay, now notice how much easier this integral is than the one we had originally. Cube root is u to the 1/3. Negative 1/2 has been factored outside. The u is still in there. So again, this is an easy anti-differentiation question, right? So let's go ahead and do that. So add 1 to the power and divide by the new power. So you're dividing by 4/3, or it's the same as multiplying it by 3 over 4. Okay, at this point, let's just simplify this. So negative 15 over 8. And instead of u, I'm going to bring in its equivalent, which is 1 minus x squared to the power of 4 over 3 plus c. Again, one way to check our answer is we can differentiate that entire quantity and show that it will give us the original question that we started with. So hopefully it's starting to get a little bit more natural, like the process doesn't look so like, what am I doing here? What am I doing there? In the beginning, there's so many components to it, right? But again, from my past experience, by the time you get to the 4th, 5th example, you see the patterns are always repeating, and hopefully it's becoming more natural, like it's not so weird like the first example maybe you may have seen on U substitution. Okay, this one would be a perfect one for you to start, so this would be a great place to pause the video a little bit and then come back and take a look at the solution momentarily. So a good choice here is to let u be 1 plus x squared. Then you would write du dx is 2x, so du equals 2x dx. I come back to the original integral, and I notice that the bottom is what I'm going to have square root of u, because 1 plus x squared is u, so you have the square root of u in here, right? Okay, on the top you see x dx, so I come down here. What is x dx in terms of the u variable? X dx is du over 2. So I can put du over 2 in here, du on the top, 2 on the bottom. But in the next step, I'll factor the 1/2 outside, and so I have du over square root of u. So much easier integral to deal with than the one we started with. Notice at the moment I'm ignoring the limits. I'm going to bring them in as my last step. And to integrate this, it would help to write it as u to a power. This is u to the power of negative 1/2. Okay, to integrate that, again, add 1 to the power, divide by the new power. Division by 1/2 is the same as multiplication by 2 over 1. So we could put a plus c, but because I know limits are along the way, so I'm not going to put the plus c right now because we're going to put the limits very soon. So the 2's cancel. We have u to the 1/2, which is the square root of u. And instead of putting u here, I'm going to put 1 plus x squared. And now the limits, 0 to 2. So all we have to do is plug in the upper limit minus the lower limit. Plug in the upper limit, you get 2 squared plus 1, which is 5. Minus plug in the lower limit, square root of 1, which is 1. So we have root 5 minus 1 as our final answer here. So let's take a look again, the steps. We had this integral. We couldn't have done it without the u substitution. There is no quotient rule for integration, right? So we had to see if it can be done with u sub. So if you let u be this quantity, its derivative is 2x dx, and there's already an x dx on the top. Therefore, we know this problem can be done with u substitution. And not too surprisingly, perhaps, every problem you're going to encounter in this section can actually be done with u sub. But as you continue to other sections, especially in Calc 2, you're going to encounter quite a few questions that cannot be done with u sub. And in that situation, you're going to be introduced different techniques of integration that can handle each and every problem that you are encountering. But the ones in this section, it's safe to say every one of them you'll be able to use u substitution. But if I gave you a problem like this, same problem, but a high power on the top. So if you let u be 1 plus x squared, its derivative is 2x dx, and notice you have x to the 5 dx. What are we going to do with that, right? At that point, you would recognize that problem cannot be done with u substitution. So it's a good idea to visualize the situations where you can use u sub versus where you are not able to use u sub. All right, one more example. Let's take a look at this one. So the integral of, and for this question, let's not even worry about the limits. Let's just integrate 5x over quantity 4x squared plus 6 to the 3rd power. So think about it. What would be a good choice for you in this case? If you said 4x squared plus 6, you are correct. Now the last few examples, we may have a few of them where you have like x dx, but it doesn't always have to be that way. As a matter of fact, the last example we had was x squared dx, so that's good. So it's not always going to be x dx, right? Okay, so let u be equal to 4x squared plus 6. And it's very important not to take 4x squared plus 6 to the 3rd power as your u, because that would be defeating the purpose of making the problem easier, because then du would be very complicated. Okay, so just the inner portion there, let u be 4x squared plus 6. Then du would be 8x dx, And ultimately, I'm going to need to know what is x dx. That's what I see on the top. So solve for x dx, which will give you du over 8. This would be a great place to pause this video and to try to finish the problem all the way to the end, and then let's check your answers in a few moments. So hopefully you did that. So rewriting everything in terms of u, the bottom will be u to the third, 5 can be taken outside, and x dx will be replaced with du over 6. Excuse me, du over 8. Right, so at that point, simplify this. Write this as u to the negative 3 du, and that will be easy to anti-differentiate, which will be u to the negative 2 over negative 2. We add 1 to the power, divide by the new power. Notice in the next step, I'm not going to have the integral symbol anymore, because once you take the antiderivative, that has done its job. It should disappear. If I had the integral symbol here, it would be wrong, and I've done a lot of corrections on the test recently. Students have the habit of keeping the integral sign a little bit beyond where they should keep it, and that would actually be an incorrect notation, so please be careful about that. Okay, so now I can multiply these two together on the bottom to get a negative 16 or negative 5 over 16. And because there's a negative exponent on u, I can also bring it to the denominator as u to the positive 2 power. So simplify your constants, you get negative 16. The negative can be put up front, and this u to the negative 2 comes to the bottom as u to the positive 2. And at this point, since I decided not to worry about the limits, I'm going to end up putting a plus c over here. And the last step is put the u back in place, and in our case u is 4x squared plus 6. Don't forget it's going to be squared, and don't forget that the constants up front will be kept the same. So 4x squared plus 6 to the second power, preceded by negative 5 over 16. And since we decided not to do the limits in this one, we're just going to enter as plus c at the end there. And at that point, if you had to do the limits, since you would do it after you brought the x variable, you draw a line 0 to 2, plug in the upper limit minus the lower limit. Okay, one last example. Okay, let's take a look at this one. The integral of 6x to the 4th times the cube root of x to the 5 plus 10. Again, this is a great place to pause the video. Think about what you would select as your u variable. Try to write the entire integral in terms of u's. Take the antiderivative, and then come back and check your work. So hopefully you've done that. So let u be equal to, I'm going to let u be this quantity x to the 5 plus 10. I can mentally do a check. The derivative here is 5x to the 4 dx, and there's already x to the 4 dx, so I know that will be a good candidate to be a u, and the problem is solvable with u substitution. And as always, as an intermediate step, we differentiate both sides, so du equals 5x to the 4 dx, and I'm going to need x to the 4 dx up there, so I'm going to solve for that. X to the 4 dx is, divide both sides by 5 here, du over 5. So going back to this integral, this whole thing will be replaced with cube root of u. 6 can be taken outside, and what are we going to do with x to the 4 dx? From down here, that will be replaced with du over 5. So let's do as we just said. So the 6 was taken outside, the cube root of x to the 5 plus 10 is replaced with the cube root of u. So this has been taken outside, so now we have to worry about x to the 4 dx, and we know x to the 4 dx is the same as du over 5. I put the du on the inside and over 5 on the outside. If you wanted to, you could have certainly put the du over 5 in there first, and then in the next step factor out the 1 over 5. Okay, now we see we have a much simpler integral that we are dealing with, right? Take a look. This seems so complicated, whereas the cube root of u seems an easy enough integral to integrate. So keep the 6 over 5, and that's the same as u to the 1/3 power, right? So add 1 to the power, you get u to the 4/3, and then you can divide it by 4/3. Now dividing by 4/3 is multiplying by 3 over 4. So keep the 6 over 5 right in there. Multiply it by 3 over 4 times u to the 4/3. At this point you can simplify a little bit, um, and you can simplify it in a variety of number of ways, but for example you could say, okay, um, this is 18 over 20, and then I can simplify 18 over 20 by reducing by 2. This will be 9, reduced by 2, this will be 10. So you can write as 9 over 10. Or you could have reduced this one by 2, you'll have a 3, this one by 2, you'll have a 2, and multiply tops and bottoms. Another way to simplify, right? Ultimately, you'll have 9 over 10 times. So all of this gave us 9 over 10. Now you have u to the 4/3, and in that situation, don't forget u has to be replaced back. So u is x to the 5 plus 10 by putting it back in place. And don't forget the power of 4/3. We still have the plus c because we did not have limits of integration in this question. If we do have limits of integration, we will remember to keep it all the way till the last step, and only after the x is brought in, that's where we're going to draw the line, that's where we're going to evaluate it. So hopefully these examples gave you an idea about how to solve problems involving u substitution. And again, the best way to really comprehend this, like any other section in math, is to solve lots and lots of questions, and by the time you complete like your infinity problem set, I think you're going to feel much more confident. See you in class.